Ladies and gentlemen, welcome to C7-3 Discs and Washers, our second component of 7-3. Remember, 7-3 is going to be broken up into 3 separate gluons. There's a lot here. And also, interestingly, perhaps this might be a reason for why it's not a beautiful day for math, is this is our second to last glue-in of new material. But it's obviously a beautiful day for math because we're still talking integrals. And we're talking about volumes of solids and calculating these volumes. So let's get right to it. Find the volume of the solid generated by revolving the shaded region about the y-axis. So we have the shaded region here. So if we revolve it about the y-axis, that means it'll be symmetrical about the y-axis. So let's see, here's the original shaded area to 3. And then that's at a y value of 2. So in order to draw these, I like to do a symmetrical region. So it's going to be looking something like that. And this is the original shaded region. That's what gets spun around. So therefore, what's created is a cone type shape, an upside down cone. And when we do that, we'll see we have a circle on top. And if we slice it perpendicular to the y-axis, we would have additional circles. So we slice perpendicular to the y-axis, we're going to have circles here. So again, circular discs. So this is reminiscent of what we did last time on 7-3 discs. However, this time we're revolving a shaded region around, and that creates this upside down cone. And if we slice it perpendicular to the y-axis, these discs have a thickness, oh, that's not dx, they have a thickness of dy. So if we pinched one of those circular disc skins, pinch it, the thickness of that skin would be a change of y. So we have a dy slice in this case. So that means when we do the integral, we need variables of y. So again, like last time, let's get together an equation for the area of each slice. So let's see, we're talking circles. So again, pi r squared. So the area of each slice is pi r squared. But again, we need to ground the equation. We need to ground the formula to what we know. So we know that we have this curve x equals 3y over 2. So let's see, we need to know the radius. So if I extend the radius out, that radius is an x value. So the radius is the x value. And fortunately, this curve that we know is already solved for x. X equals. So part of the work's already done for us. So the radius is not just r. We want to ground it towards this equation. So area equals pi, and then the radius, again, here's the radius. The radius, this length is x. So it's the x coordinate on this curve. X is 3y over 2 squared. And look at that. We have dy slices, and this equation's already in terms of y. I'm just going to clean it up just to see what we have here. So let's see, we would have 9 pi y squared over 4. Let's make sure I did that right. 3 squared, yeah, okay. So that's looking good. So the area of each slice is 9 pi y squared all over 4. So let's see, we are slicing. We slice perpendicular to the y-axis, so we slice from 0 to a y value of 2. So we're going to be doing the integral from 0 to 2. of 9 pi over 4 y squared, and then these are dy slices. And I'm going to do something a little funky here. I'm going to factor out that 9 pi over 4 from the integral. And all I'm left with is simply y squared dy. And then importantly, we have to see that all of that integral is in a Texas size bracket. So this nasty chunk stays by itself. So it's all, whatever happens with this integral gets multiplied by 9 pi over 4. So let's see. Let's do the fundamental theorem of calculus. So let's see, 9 pi over 4, and then a Texas size bracket. And now we can untangle this integral. So it's 1/3 y to the third plus c. And then we're going to evaluate that integral from 0 to 2. All right. And then let's just proceed with the fundamental theorem. So 9 pi over 4. And now we can plug in 1/3 to the third, 2 to the third plus c minus, and then let's do a bracket inside a bracket. That 3 is bothering me. So, and then good thing I checked because that is a 1/3. And then let's see, minus 1/3 0 squared plus c. And then close off the double bracket. So all that's gone because that's just 0. So we have 9 pi over 4. The c's cancel. And then we have times 1/3 times 8. Ugh. So let's make sure we did that right. All right. So then it's 72 pi over 12. Which, let's see, 72, let's see, 36 over 6 pi, therefore, it's 6 pi. Let's see, volume, units cubed. So, the volume of that revolution, that volume of revolution is 6 pi units cubed. Boom, page 1. Let's go to page 2. So on problem 2, instead of revolving about the y-axis, we're going to revolve about the x-axis. So our work starts by drawing a picture. So since we're revolving about the x-axis, that means it's going to be symmetrical about the x-axis. So I always start by drawing the original region. So there it'd be. And then just give it a light shade. So there's the original region, and then it's going to be symmetric about the x-axis. So I'm going to draw that symmetrical region. And give that a little shade. But that's been spun about the x-axis. So we really kind of have a cylinder hanging out there. And then that's the bottom. And then if I do a cylinder in the middle, or excuse me, if I do a slice in the middle, if we slice there, notice how we're slicing perpendicular to the x-axis, so therefore if I pinched one of those slices, it would be dx thin. The thickness would be the change in the x-axis, so dx. So this is a dx slice. And notice how the shaded area is what the solid is. So really we have like a cylinder on the outside, but then inside that cylinder a cone has been bored into that solid cylinder. So this cone is hollow, and then what you see here kind of shaded is the actual whatever material is here. So it's a cylinder. Let's see, maybe that'll help. Maybe let's draw the top of it. So we have a cylinder on the outside. If you just looked at it from the outside, it's a cylinder. But on the inside, a cone, three-dimensional cone, circular-based cone, has been bored out of the inside of this solid cylinder. So then we have kind of like a funnel, if you will. But importantly, we really have a disk that we need to find the area of. Before, when we sliced, we got just solid circles. Now, when we slice, we have this solid area, but on the inside, it's hollow. So I'm going to pull one of those slices out. Let's see, that center needs to be a little bit up higher. So, we have a big circle, and that big circle has a radius of big R. And then there's a little circle, starting from there, there's a little circle, and that circle has a radius of little r. So if I color this, this is a washer, so that's hollow. So really, I need to find the area of this material on the outside. So really, to find the area of the washer, I need the area of the big circle, so pi big R squared minus pi little r squared. So if I find the area of the big circle and then subtract off the area of the little circle, then I'm left with the remaining material. So if we notice, let's see here, we need big R, so from the middle, so from the x-axis up, the outside, the big circle is always having a radius of 2. That big circle always has a radius of 2. So if I start plugging in, the radius is 2. So now I need to tease out what is the little radius. So the little radius from the ground up, so from the x-axis up, is up to the curve. So the radius here, so from the x-axis up, is actually the y value. So from there up, the small radius is actually the y value. So it'll be pi y squared. But we're doing dx slices, so this y is no good. And okay, let's see, we have x equals 3y over 2. So, okay, so that means I need to solve for y. So 2x equals 3y, which means y equals 2/3 x. Okay, so now I can substitute in for y, and now my equation is in terms of x, which is great because these are dx slices. So pi, and let's see, 2/3 x squared. And feeling a little lazy right now, I'm going to do this using the calculator. So I'm going to type in the equation. So let's see, that's 4 pi minus pi, and then in a parentheses I have, 2/3 x squared. So let's see what we got here. I might just put this 2/3 in a parentheses just in case. All right, so I'm going to take the integral of this. Oh, we're not even there yet. So that's the area formula for each of these washers. So like we've been doing before, we're going to take the integral, and now that we have this formula, so we're going to take the integral, and let's see, we're doing dx slices, so we have to go from 0 to 3, and then 4 pi minus pi, let's see, I guess I can simplify this, so 4/9 x squared, and then these are dx slices. So now I can find the integral. It's going from 0 to 3, just make sure that's right. All right, so then fn int math 9 vars, y vars, typing this all in, going from 0 to 3, and I get 25.133, which I feel like let's see. I feel like that's going to be something prettier because this is we got circles, we got washers. I'm going to divide by pi. Right. It's 8 pi units cubed. That's cleaner. So the volume of this cylinder with a cone bored into it, its volume is 8 pi units cubed. All right, you are now ready for 7-3 discs and washers. Enjoy.